All right, the recording is started. So we continue on with the last summary lecture of the second part of the physics foundation for EEE. So just a recap of what we did last week. We covered two topics. First topic is on magnetic fields. So we discussed how a magnet around magnets, we can have magnetic fields, and we can visualize a magnetic field using these magnetic field lines. So the magnetic field and magnetic field lines, these are, similar to how electric field and electric field lines are used for showing how the effect of having positive and negative charges are in space. So this is for magnetic field is for having magnets in space and how that affects the surrounding space. So when you have magnetic force and you have a moving charge inside a magnetic force, when you have a magnetic field and when you have a moving charge inside a magnetic field, then it can create so-called magnetic force, and it is given by Q is the charge is the charge, and V is the speed of the charge moving, and then B is the magnetic field. So they will all act normal to each other. So you can use your right hand rule to figure out which direction the force is going to act. Okay. So when everything is 90 degrees to each other, you can just do a simple multiplication of all the quantities. Whereas if the V and B is going to be at an angle, then your force is going to be smaller than multiplying all together. You need to use you need to put sine theta after multiplying all the three quantities. Okay. So because you have force acting on a charge when the charge enters into a uniform magnetic field with a given velocity, it's going to be moving in a circle, having the magnetic force acting as a centripetal force to this circular movement. So we've discussed about this. And when you have a current carrying wire, because current carrying wire means there are many charges moving across that wire, then if that is placed under a magnetic field, then it's also going to have this magnetic force, and that's going to be magnetic force due to current. Current is moving charge, right? And that force can be calculated using this equation. Again, you have this cross product between the two vectors. This L vector is pointing to which direction? It points to the direction of the current flow. Okay, because you have a long wire, that means either current is going to be flowing in one direction or the other direction. So which direction does it flow? It has to flow in the direction of the L vector has to be pointing towards the direction of the current flow. Okay, and B is of course the direction of the magnetic field, and do a cross product, gives you the resulting direction of the resulting force, and that would be again, you can use your right hand rule to figure that out. So that was the first part. The second part is now how is that this magnetic field is created in the first place. One way to create magnetic field is when you have an electric current flowing, then that will create magnetic field around it. It will curl around the flow of the electric current, and you can use your right hand grip rule to figure out in which direction the magnetic field is going to curl around that electric current flow. Okay, so you place your thumb in the direction of the current flow, and then the direction of your fingers, which is going to go around your thumb, will be the direction of the magnetic field. Okay, so everything is done with your right hand. The cross product for calculating the magnetic force and also calculating the magnetic field, you just use your right hand. And so just make sure you don't use the left hand when you are trying to solve this kind of questions. Okay. All right. So because the current flowing current carrying wire will have magnetic fields formed around it. For instance, if we have this is current coming out of the page, this is current going into the page. If you have such an arrangement, and then you put a closed loop around it, and then you calculate, because that will cause magnetic field to be created around the wire, whether it is in the clockwise direction or the anti-clockwise direction. When you take the line integral of a closed loop, then Ampere law says that that would be proportional to the total net current that is enclosed within this loop. Okay, so that's what Ampere's law says, is that if you calculate the line integral of the magnetic field just around there, with small ds just going around and closed in a closed loop, so with that circle there, and that's going to be proportional to I, and that proportionality factor is going to become be the permeability of free space, which is this number. I think that number is a constant. So this is a constant number, which you can refer to your constant formula sheet. Okay, so that's Ampere's law. And now we look at, we also discussed about Gauss's law in magnetism. If you remember Gauss's law in electricity, it was that within a Gauss, if you have a Gaussian surface, right? Gaussian surface means closed surface that encloses a volume, totally complete surface that encloses a volume. And then the total net flux going through that surface, Gaussian surface, is going to be proportional to the total net charge enclosed in that Gaussian surface. That was the Gauss's law in electricity. Now Gauss's law in magnetism is going to be the same concept. Now, if you calculate the total magnetic net flux through that Gaussian surface, enclosed surface, then it's going to be 0. Now, why is this different from the Gauss's law in electricity? In electricity, you can have individual positive and negative charges. You can have them isolated, separated. Whereas with the magnetic poles, north and south pole, they always come in pair, means that if you have a north pole here, there must be a south pole inside the Gaussian surface, okay? So that means all these lines, because these lines originate, it starts from the north pole and then it ends in the south pole with a magnetic field. So all the lines that goes into the Gaussian surface must come out, okay? Because there's no any south pole to terminate the line, nor there's any north pole that can start any new line inside this Gaussian surface. That's why it's going to be 0. And Ampere's Maxwell's law says, so this is Ampere's law, but then Maxwell came up with some additional term, some correction term to this Ampere's law, which adds what? Which adds that any time-varying change in the electric field that is going through the Amperian loop. So if through here, through this Amperian loop, if there is any change in the electric flux through this Amperian loop that changes with time, then that's also going to create magnetic field. That's Ampere-Maxwell's law. So there are two factors that can create magnetic fields. First one was the constant flow of electricity, constant flow of current, electric current. And then the second one is the electric flux that is changing with time. So there's the AC component, we call it AC component, and then we also call it a DC component. This is going to be the DC component. This is something that is AC component, because if something changes with time, then that would be, alternating with time, let's say. Okay. So that's what we did last week. Any questions on the recap? Comments? Okay, I will move on. Okay, so we have 3 topics to cover. First is Faraday's law. Second one is the law of induction, or inductance, I think. Yeah. I mean, Faraday's law is law of induction, and second one is the inductance, and third one is electromagnetic waves. So Faraday's law is on how to create electricity, or how to create electromotive force. So how do we generate electricity? Is it's based on Faraday's law, basically. Okay? So shall we say EMF? So EMF, in fact, is a very similar to electric potential, but and it is the same unit. It's measured in the same unit, but it is how much the electric potential is created. Okay, as opposed to how much electric potential is needed to, which it was the electric potential, but how much potential is created through, in this case, changing the magnetic flux through certain closed loop. But okay, I will continue to talk about Faraday's law. So EMF induced in a circuit. So EMF, it will be induced in a circuit when there is a change in the magnetic flux through the circuit. Okay, so let's say this is a circuit. So I created a circular circuit, okay? And then I place that loop, the circuit loop, inside a magnetic field. And then if I change the size of the magnetic field with time, then that's going to create a current flow in that loop. Okay, so this is how you can create electricity. Okay, or create current flowing, and that current flow is caused by the EMF induced. Okay, the electromotive force or the voltage that is induced. So from this, we know that we can induce EMF either by changing the size of the B, So because when we change the size of the B, then we know the flux is going to change. The flux going through flux. Remember, flux is the total number of arrows that is passing through this loop, right? So that's going to change. Or we can try to change the area. How do we change the area? I mean, yeah, we can either try to reduce the circuit or with time. It has to change with time. Of course, I have to keep emphasize that. Or we can change the angle. When we change the angle, the effective area or the area that is perpendicular to the flow of B, the direction of B is going to change, right? So that's also going to change this dot product. So that will also induce EMF. And then any combination of these 3, in fact, is going to give us electric potential, create electric potential around the circuit. There. Okay. And if we have not just one loop, but we have so many loops, then the potential created is going to be multiplied by number of identical loops that is there. Okay, so if we like wind it up into something, then it's going to create a lot more electric potential multiplied by n. So then the question is, in which direction the EMF is going to be induced? Okay, so let's say we have a magnetic flux that is going in the upward direction through the loop, in this case, okay, through the loop. And then we are increasing our magnetic flux. So when the magnetic flux is increasing with time, then in order to find out in which direction this EMF is created or in which direction the current is induced, we need to understand the Lenz law. Okay, what Lenz law says is that the current produced will try to counter the change, oppose the change. Okay, so here the magnetic flux is increasing with time, so it is getting stronger going upward. Okay, into the upward, going into the upward. Now, then the current will be produced in such a way that trying to oppose this change. So in which way we need to create the induced magnetic field? It must be created downwards. Okay. And in order to create a downward magnetic force, magnetic field, then in which direction should the current be flowing? You use your right hand grip rule, and then it's pointing. Circulate. It must be circulating in the clockwise direction, right? So that's how the current will be produced when we have an increasing magnetic flux going upwards with time. Okay. Now we have another case. We still have magnetic field going upwards, so we haven't changed the direction of the magnetic field. But now this time we have decreasing magnetic flux through this area. Okay. Now, because now that it is decreasing, we try to oppose the change, or the system is trying to oppose the change by creating more induced magnetic field going upward, right? So because it doesn't want to change, it somehow tries to oppose the change. So in order to create the field, magnetic field going upward, then in which direction the current needs to be induced? It needs to be induced in the counterclockwise direction. Okay. So basically what Lenz's laws is telling us is that the system tries to maintain the original flux. And in order to maintain that original flux, the direction of the current flow has to be in certain way. Okay, because the current flow in a loop is going to create magnetic field. Right? So that's how you can figure out which direction is moving. So let's take a look at this example. We have a rectangular conducting loop like that. It's placed near a long wire carrying a current I. So this is current I flowing this way. If I decreases with time, okay, in which direction is the current induced in the loop? Okay, so if I is flowing this way, now you use right hand grip rule. In which direction is the magnetic field inside this, or which way is the magnetic flux through this rectangular loop? It's going to be into the page, into the slide, right? Into the page. To be into the page. Now, when this is reducing, when I is decreasing, this flux going into the page is going to decrease too. Do you agree? Yes. So it will decrease. Then when that decreases, the system will try to create a flux that is going into the page in order to maintain that, right? In an attempt to maintain that. So how do you create a flux that is going into the magnetic field that is going into the page? By letting the current flow in the clockwise direction. Use your right hand rule, right hand grip rule, and know that your fingers must be pointing in the clockwise direction in order to create more magnetic field going into the page. Okay. So I hope you get the idea this way. So I have written it down. Yeah, so you can take a look at that if you are still confused. So what's very important is the change in magnetic flux. That's the important bit. It's not actually which direction the magnetic field is now. The important is in which direction the magnetic field is changing. The flux is changing. Is it decreasing this way, or is it increasing this way? Or that's more important. And then the thing is that the Lenz law is that it will try to maintain the original flux. Okay. So then the induced current will be in such a way to do that. So that is one way to create or induce EMF or induce current flow. Another way to create EMF is to use so-called motional EMF. Okay, so how do you do that? If you have a magnetic, if you have a conducting medium, if you have a conducting material, and then you move it across the magnetic field, like shown in this picture here. Okay, so what are we going to get? We're going to get, actually, because in because inside the inside the conductor we have electrons, right? And of course we also have nucleus, which is positively charged. But electrons and positively charged nucleus, they will all experience force because what you have is a moving charge. Okay, so all the nucleus will be moving in this direction, V, and all the electrons will also be moving in this direction. But that means then the charge is moving. The negative charge must be moving. If the negative charge is moving in the right hand, towards the right, that means Q times V is going to be towards the left, right? So in which direction is the force going to act on the electrons? Which direction is the force going to act on the electron? The force is going to act. You need to use your right-hand rule. So your V is QV, negative QV is going to move into towards the left. Okay, and then your magnetic field is going to go towards the into the page, and then your force is going to be acting downwards, right? So that will eventually move all the electrons downwards. How about the nucleus? Can you move the nucleus? No. Okay. You cannot move the nucleus because it's a solid material. They are all fixed. The electrons still can move because they are all in so-called conduction band. This is a conductor. In conductor, electrons are free to move. So electrons will in fact they will all come down. Okay, all come down, but nucleus will all stay in their positions. And what that means is that relatively, the top part will be more positively charged because there are less number of electrons there. Then there are more number of electrons there, so there will be negatively charged on one side. So when we keep moving it, would this continue? Would this movement continue? No. In fact, it will stop at one point. Why it would stop is because as the electric field, electrons accumulate at the bottom here, and then electrons, there are deficit electron deficiency at the top there. That means the electric field also is going to be created this way. Okay, electric field is going to be created that way, and that means these electrons will not only experience the magnetic force, but it will also experience the electric force, or the Coulomb's force, due to the field created between these two polarities. So that means at one stage, once there are enough accumulation of electrons there and enough deficiency of electron there, then these two forces will balance, and then that will actually stop any further movement of the electron. So even if you continuously keep on moving, once certain level of accumulation of electrons and deficiency of electrons is reached, then that will stop there, and then that is given by this equation. So you can actually calculate the electromotive force created by this motional EMF using this equation. And of course, in this case, this would be for everything at 90 degrees. So one way was by increasing or decreasing the flux going through a loop, a conducting loop, and then the other way was to move a conductor across inside a magnetic field, and it will also create that EMF. Okay. So let's take a look at induced EMF and electric fields. So this was Faraday's law, how we can create the EMF by changing the magnetic flux going through a loop with time. So it changes when that flux changes with time, then we can create EMF. Then we also know that this EMF is the electric potential is actually given by the electric field the line integral of the electric field around a closed loop. Okay, so we can equate these two together and then come up with this equation. And then this equation, as you can see, so what this equation means is that if you take a line integral of electric field around any closed loop, okay, any closed loop, line integral of the E and the electric field and that line around any closed loop is going to be equal to the time rate, the rate of change of the magnetic flux that is going through that loop, the closed loop, okay, bounded by the loop. Now, this actually is quite similar to what we discussed before, and which is for if you take a line integral of the magnetic field and the line around surrounding it, then that will give, according to Ampere-Maxwell's law, that would be proportional to the current that is going through, the DC current that is going through the loop, plus the time changing electric field, electric flux through that loop. Okay, so you can kind of see that if we don't have any current going through, that Amperian loop, we're going to have, in fact, a very symmetric system. So what we are going to have is, if a flux going through the loop, if the electric flux going through the loop changes with time, then we're going to have magnetic field created. Likewise, if we have a magnetic flux that changes with time in the loop, then we're going to have electric field created. That's actually a very important consequence of these two equations, which we're going to see why it's important. It's actually important for electromagnetic wave, which is the light. Okay? So we're actually going to take a look at that later on. So that summarizes the first part, which was on Faraday's law. So remember how we are able to generate EMF using changing magnetic field with time around the loop. Okay, and the direction of that induced current is going to depend on the Lenz law, which is which tries to oppose the change. And then, of course, also a conducting medium moving inside a magnetic field can also create EMF. This is called motional EMF, and then you can calculate it using this equation. Then we also discussed how changing magnetic field through the loop can create electric field around it, which is going to be an important factor when we discuss the electromagnetic waves later. Any questions up to this point? Okay. So we're going to talk about inductance, and let's talk about what inductance means. Okay, let's take a look at this example. This is an open circuit, so I have a battery source. And then it's not connected yet, but I have a resistor, so that's the simplest circuit that we can have. And it's open, so there's no current flowing. Now, as soon as I close it, it's on state now, then the current will flow this way, right? Now, current is flowing in this case, in which direction? It's flowing in the anti-clockwise direction. So I use my right-hand grip rule, then I can find out what's going to be the magnetic flux inside this loop, right? What is it going to be? It's going to be coming out of the page, right? It's coming out of the page. But then what we have just done here is that we had no flux going through the loops. Of course, there's no magnetic flux because there's no current flowing. And then we now just created a flux that is going through, coming out of the page, right? Now that changed with time because when I press the button or press the switch, that changed with time, right? So if the flux going through the loop changes with time, what happens? It induces current, right? This is Faraday's law, right? So it will induce the current in which direction? Such that this magnetic flux change, which increased in coming out of the page direction. So we need the induced magnetic field has to be going into the page, right? Because we have to oppose the change, or the system has to oppose it. I'm not trying to oppose the change, but the system has to oppose the change. And in order to create the field going into the page, which direction the current needs to flow? It needs to flow in the clockwise direction, right? It needs to flow in the clockwise direction. So this blue battery is the induced EMF. It's the induced EMF due to me suddenly letting the current flow. Okay, so this is called induced EMF. And if I was to draw how the current, and you can see that this induced current EMF creates a current that opposes the change, right? That opposes the change. But what would happen eventually to this one? It would die down because, of course, I mean, this change in magnetic field happens with a very relatively small, short time, and soon after, we actually reach this state, right? So then this I induced will reduce with time, and then this I will dominate, and then that will be it. And then this induced EMF is also going to go to zero, right? So if I draw how the current is going to flow inside this circuit, this is part where the switch is open. Now I close the switch, so I switch it on, right? And then the current doesn't immediately jump up. That is because when we close the circuit, right? When we close the circuit, there is this induced EMF created, and then that creates induced current, which opposes this flow of the current this direction. So it, rather than jumping up like that, like my dashed line, it actually follows this red curved line, which increases slowly, not slowly, but it increases with time. Okay. And that, of course, it will eventually reach the final state where this I induced is going to be zero, and but it will until that time is reached, it will increase slowly like that. So this epsilon L, which I drawn in blue, is called the self-induced EMF. Okay, this is called self-induced EMF. And why is it called self-induced EMF? Because this EMF is created by itself because it was trying to oppose the sudden flow of the electric current, which created the sudden increase in the magnetic flux. Need to oppose that, and then this is called self-induced EMF. And because it always opposes the direction of the battery, right? Because I always opposes the direction of the current flow, is also called back EMF. So it's equivalent. Self-induced EMF or back EMF, they are the same thing. Any questions? Any questions on this part? Okay. All right. I think we move to the next part. So let's look at this coil example, right? Let's look at this coil example. Now, current is flowing in the black arrow direction. So if the current is flowing in this black arrow direction, then in which direction would we have the magnetic field? Magnetic field is going to be created. You need to wrap your fingers around in the direction of your current, then magnetic field is going to be created in this way. So this side, this is going to be an electromagnet. This side is going to be north pole, and that side is going to be south pole. Can you picture that? Okay. Now, so we had that. We had this current flowing, but now we somehow from our power supply we increase the current flowing. Then what will happen? This magnetic field going in this direction is going to increase, right? It's going to increase. Now, then that will create induced EMF. And that induced EMF will be created in the direction that opposes this change. So we need to create a current such that it will induce induce the magnetic field in the opposite direction. Okay, it will induce the magnetic field in the opposite direction. And in which direction should the then induced current be flowing? It should be flowing in the opposite direction. So it should be flowing in this direction. Okay, like that. Okay, so that this blue line is the induced current, and this is the induced magnetic field, and this is the induced EMF across this coil. Okay, now let's look at an example where we have decreasing I. So everything is the same. Everything is the still current is flowing this way. So we have a magnetic flux field going this way, so that we still have this north pole and that south pole. But now we reduce the current with time. We slowly reduce the current. And what will happen is, because this now flux is reducing, flux through the coil is reducing, it will try to induce more current such that it will create more magnetic fields going in this direction, towards the left, meaning induced magnetic field also going to have north on the left and south on the right. Okay, south pole on the right. And then that means induced current is going to have to flow in the same direction, in fact, as the electric the actual current that is supplied from the battery. Okay, and then induced EMF is going to be in the same direction also. That's because we were decreasing the current, whereas this was in the opposite direction because we were increasing the current. Okay, so again, this comes from the Lenz law, which says induced EMF opposes the change in current. And this induced EMF can be calculated using this equation where N is the number of coils. So this one, I mean, you can start counting, maybe 12 or something. Will be induced EMF will be proportional to the number of coils that you have, as well as the change in time, change of the flux with respect to time. How quickly the magnetic flux changes will give you how big this induced EMF is. So if you want to create very big induced EMF, what you need to do is you need to change your current very quickly, in less than a second or something. Then it will change, it will create very large induced EMF. And that this is the change of the current, and how much EMF is induced per rate of change of electric current is going to be dependent on the general geometry and shape and all that stuff of this coil. Okay, and that is called the inductance. So inductance is given by this this system itself, how it is shaped and what sort of material is there, and is there anything, is this a vacuum or is this filled with some other material? That's going to depend on the inductance. I mean, that's going to give how big the induced EMF is going to be, and that is called inductance of that system or this system. Okay, and it's measured in Henry, and 1 Henry is equivalent to 1 volts second per ampere. This is the SI unit for the inductance. So because we let's look at this example here, right? So when we initially didn't have any current flowing, and then we suddenly close the circuit, and then current is flowing, but the current didn't flow immediately. It started flowing immediately, but it didn't jump to the what it should be immediately. So during this time, where did that energy go? Because we supply enough energy from the cell, but then energy just disappeared during this time. That energy, in fact, was used in creating the magnetic field. So that magnetic field, in fact, is storing the magnetic field is storing the energy, the energy that that was lost because the current wasn't actually jumping to the maximum from the beginning, right? So that means that magnetic field and that magnetic field is around the inductance. So and the strength of the magnetic field that forms around the coil is going to depend on the inductance, okay, the size of the inductance. So we can calculate, in fact, from that how much energy is stored when we are operating that inductor, how much energy is stored in that inductance, that inductor, okay? And this is similar to how we were able to calculate how much energy is stored in the capacitor. You remember, like, when we charge up the capacitor stores the energy in the form of what? In the form of the electric field. Because when you charge up the capacitor, because the current doesn't flow between the capacitor, but there is an electric field that is forming in between, right? And that field contains the energy. The energy stored in that field. So likewise, you can store energy also in the magnetic field. And how much energy is stored in that? You can use these two equations. So it depends on the capacitance in the case of how much energy is stored in the capacitor, and it also depends on the inductance in terms of figuring out how much energy is stored in the inductor. Okay. So you can use that equation. So in a capacitor, electric field is established between the two plates in the process of charging, and energy, we can say that energy is stored in the electric field. And this is how we can calculate the energy stored in the electric field. And likewise, in an inductor, it creates a magnetic field around it, right? And it establishes a magnetic field in the process of driving the inductor. And the energy is also stored in, that means the energy is stored in the magnetic field. And you can say that it is stored like that. Now you can kind of see a symmetry between the two systems, right? It's both the energy stored is both proportional to the square of the field strength, E and B field strength, and then it involves some sort of vacuum constant. Then there's the half factor there. See the symmetry. So that summarizes the second part. Remember how the induced EMF is created in a coil, and then from that we can figure out what the inductance is going to be. Okay, and inductance again is measured in Henry. So inductance is the proportionality factor where the change in the current with time, with respect to time, is going to create the EMF, the induced EMF. That's going to be the proportionality factor. How much it is good at creating the EMF with small change in, or just a small change in current with time. And then we can calculate the energy stored in an inductor using this equation. Likewise, we can also calculate the energy stored in a capacitor, which was covered in earlier lectures. And then from that, we can also figure out how much energy is going to can be stored in an electric field and magnetic field. it is important to note that this the energy stored is proportional to the electric field strength square, and also magnetic field strength square, and then there is some symmetries. All right. So, questions up to this point? Or comments? All right. I think I'll move to the last topic. Okay, so electromagnetic wave. So we have covered so many equations up to now. We had Gauss's law, we had so many different equations, but James Maxwell, actually compiled all these different studies together. Then he compiled it into 4 very important equations in electricity and magnetism. Initially, people thought electricity and magnetism, they were different, 2 different effects. But of course, through Faraday's law and Ampere-Maxwell's law, we know that they are linked together because magnetic field flux leads to electric field, and electric field or electric flux leads to magnetic field. So, okay. So then later on, of course, then from these studies, people found out that they are somehow related. And in fact, as we saw from the source of magnetic field, it is actually the flow of current or moving electric charge that creates the magnetic field. So that it's actually magnetic field itself comes from the presence of the charge. Okay, and we all know that also electric field also comes from the presence of charge, because that is how we that came from the fact that the opposite charges are attracting each other, and and the like charges are repelling. There are force between the different electric charges, right? So that lead to the concept of electric field, and then the electric field, changing electric field led to the concept, or moving charge also led to the concept of magnetic field. So everything actually just came from the presence of the charge and movement of the charge. Anyway, so Maxwell compiled everything into these 4 key equations in electricity and magnetism. So we talked about Gauss's law. This is how the Gaussian surface, the flux through the Gaussian surface is going to be proportional to the net charge enclosed in that surface. Gauss's law in magnetism is the net magnetic flux through a Gaussian surface is going to be 0 over time. And Faraday's law was how changing magnetic flux through a closed loop is going to create electric field around it. And then Ampere-Maxwell's law was how changing the electric flux through a closed loop and a steady current through that the same closed loop is going to create a magnetic field around it. Okay, so that's the Maxwell's equation. Now, if we let me go to the next slide. Hold on. All right. If we assume vacuum or air, even air is very similar to vacuum. Okay. If we assume vacuum, then we know that there are no charges because if we are in a conductor, of course there are free moving charges. But if we are talking about vacuum, there are no charges. There's also no conduction current. There's no any current. So we can set Q in and I to be 0, and we have this equation, these 2 equations, Gauss's law and Gauss's law in magnetism with 0, 0. And then we have Faraday's law with this, and then Ampere-Maxwell's law with this, where we don't have I now. We don't have any DC component. And this is called Maxwell's equations in free space. Okay. Now, this is this is very symmetric, right? You have the Gauss's law and Gauss's magnetism law is eventually the same. And this one also, you can kind of see that there's a symmetry of how changing magnetic flux is going to create electric field, and how changing electric field is going to create magnetic field. So what this means, especially these last two, is that the time varying field of one kind is going to induce the field of the other kind, okay? And whatever it is, it will. So if something changes with time, the other will also be created, okay? So that's what that means. And that actually leads us to electromagnetic wave, okay? So in electromagnetic wave, electric field and magnetic field fluctuate in time, and it fluctuates sinusoidally like that. Okay, and they fluctuate perpendicular to each other because all these laws, when we discussed, they were the cross products, right? So they had to be perpendicular to each other. Okay, and they are also perpendicular to the direction of the wave propagation. So if E is upward, for instance, then we know, and then the magnetic field is into the page direction. In which direction would the direction of the propagation of the wave is going to be towards the right. So you still need to use your right hand rule to figure out which direction the light is going to propagate. So in free space, these strengths of the electric field and magnetic field is related by this relation, where C is what? C is the speed of light. Speed of light, and it's given as a constant. This is actually an exact number. It travels in vacuum with this speed, which is very close to 3 to the power of 8, 3 times 10 to the power of 8 meters per second. And actually, this is actually an exact number. And anyone know why this is an exact number? That's because 1 meter itself is defined from the speed of light. Okay, so 1 meter is defined from the speed of light. So speed of light is just going to be exact number. So why is electromagnetic wave important? Because it is the basis of all the wireless communication, radio communication, as well as all the light coming from the sun and all that. They are all electromagnetic waves. They are electromagnetic waves of different frequencies. What is a frequency? Frequency is how often, how quickly this oscillation happens, right? It oscillates sinusoidally. And if you have something that oscillates very fast, then that would be high frequency electromagnetic wave. If you have something that oscillates slowly, that will be low frequency electromagnetic wave. And because it is traveling at a constant speed, c, no matter what the frequency is, then high frequency means you're going to have long wavelengths. Because high frequency means you're going to have short wavelengths, because if something oscillates very frequently, and then its speed is always the same, then in each oscillation, how much it has traveled, the wavelengths is going to be very short. Whereas if something that is less frequently oscillating, very slowly oscillating, then in each oscillation, the amount, the distance that the wave has traveled would be much longer, so the wavelengths would increase. Okay, so in fact, the visible range visible range is actually very narrow. Something that we can actually see, the light, what we see is going to be is actually very narrow. It's just between about 380 nanometers to 750 nanometers, with 750 being close to red and 380 being close to violet. Okay, so you get the rainbow color. And anything that is below 380 is called UV, ultraviolet. And anything shorter than that, you also have X-ray, which you can use to get the image of your bones and stuff. And then anything shorter than that is gamma ray. So these X-rays and gamma rays, if you are exposed too much to them, not very nice, because they are very high energy. They're very high energy waves. Okay. And on the other side, you have infrared. That means more than red. Ultraviolet means more than violet. Right? Or infrared means smaller than red. And microwave, you have microwave and then radio waves and non-radio waves and so on and so on. So that's the electromagnetic spectrum. Right. So let's talk about the energy carried by electromagnetic waves. So the energy carried by electromagnetic waves can be calculated by using Poynting vectors, right? So if you see this Poynting vector, it is actually a electric field cross the magnetic field. And these are, of course, these are vector quantities. That means S also is going to be vector quantity. And in which direction is this energy carried by the electromagnetic wave pointing to? If you remember, here, the direction of wave propagation is E cross B. So the Poynting vector is also going to be pointing to the direction of the wave propagation. And this is the energy carried by the EM wave. Now, one thing that we should always remember is E and B are oscillating, right? So when E is 0, B is also 0, because you can see from this arrow that when E is 0, B is also 0. When E is maximum, B is also maximum, right? E and B, they are oscillating together. That means when the Poynting vector X is also going to be oscillating, just like how E and B are oscillating, right? And when E and B are 0, meaning right there, when now is 0, right? Now is 0, and so on. S also going to be 0 at that point. And when E and B are maximum, that means S, the Poynting vector, also going to be maximum. So you can see how it's going to oscillate. Okay. So the Poynting vector direction is in the direction of the wave propagation. I've said that. And its magnitude is the rate of energy flow. So this Poynting vector is measured in watts per meter squared. That is how much energy gets shown onto a unit area of surface due to this electromagnetic wave is what this Poynting vector is indicating. Okay, and it is measured in watts per meter squared. So how much energy per unit area. Okay, and the intensity is actually going to be the average of the Poynting vector, and that is the average power, because you remember we just discussed that the Poynting vector is also oscillating with time, right? It's oscillating with time because E and B are all oscillating. So when E and B are 0, S is 0, and when E and B are maximum, S is also going to be maximum. So we can also calculate the average of that, okay? Because it's something that is changing with time. So if we calculate average, it's just going to be something that is constant. So that gives us the intensity of the electromagnetic wave, or intensity of the light. Okay. So how bright this light in my room is the intensity, and that depends on the strength. Of course, that depends on the S vector, and that depends on the strength of the electric field and magnetic field that is oscillating while it is traveling to brighten my area. So I think earlier on, we talked about how electric fields can store energy, right? In capacitor and so on. So that equation, we can also use it to find out how much energy is stored in the instantaneous. So here, why I call it instantaneous? I call it instantaneous because E is a time varying field. It changes with time, right? That means this energy also is going to change with time. So how much energy is stored in that electric field is going to change with time, okay? And same with the magnetic field. Magnetic field changes with time, so we can also, when we calculate the energy stored in that magnetic field, is going to be changing with time. Okay. Then the instantaneous energy stored in the electromagnetic wave itself, because electromagnetic wave has electric field and magnetic field, it's going to be added. You need to add them together, and again, you need to add them together. These two are all changing with time. That means that the energy stored in EM wave itself is also going to be changing in time. We know that when electric field is maximum, magnetic field is also maximum. So when these two are maximum, that also is going to be maximum. When these two are zero, that also going to be zero there, right? And that means we can, and because the energy stored in electric field and energy stored in magnetic field is going to be the same if the wave is propagating in the vacuum, we can either say that the energy in the electromagnetic wave is 2 times that, which is this, or 2 times this, which is this, and they are going to be the same. Okay, and we can also calculate the average energy density in the electromagnetic wave. Remember, this is something that changes with time because we have sinusoidally varying fields. So energy will change with time, but we can also calculate. We can average it up, and then we can calculate the average energy density in the electromagnetic wave, and the equation is going to be that. And you can actually figure this out from this whole equation. So that, I think, we have an example here, right? So let's take a look at this example. At a fixed point P, the electric and magnetic field vectors in an electromagnetic wave oscillate at an angular frequency omega. So let's say this point is P, this point, that point is P. It's oscillating with time at a frequency, angular frequency omega, right? At what angular frequency does the pointing vector oscillate at that point? So in order to do that, so we can say electric field is oscillating with cosine omega t. You can actually forget about this kz part. This doesn't have to play anything here. But you know that if something is oscillating with time, it's going to oscillate at an angular frequency of omega. And the magnetic field is also going to be oscillating at the same angular frequency, right? Because they are always in phase, or they're always oscillating together. Okay, so the pointing vector is just going to be the cross product between E and B. Okay? And because E and B are 90 degrees to each other, they are normal to each other. So we can just do a simple multiplication if we are only interested in the size of, or the magnitude of the pointing vector. But we know what the direction is going to be. The direction is the same as the direction of the wave propagation, right? Then if we multiply these two together, we end up having this for the magnitude of the pointing vector, which is cosine squared. And if we use this trigonometry identity, then we can know that the S vector, or the pointing vector, is going to be oscillating at 2 times the oscillation of omega t, oscillation of the electric or the magnetic field. So pointing vector always oscillates at 2 times the frequency of the electric and magnetic field. And that actually is quite obvious, because you see here in this case, you have electric field going positive and negative, positive and negative, and positive and negative, right?
But if we are multiplying this, because here we said S is E times B, right? If we do that, when electric field is positive, magnetic field is also going to be positive, for instance, right? So, and when electric field is negative, magnetic field again is going to be negative. So when you multiply them together, you will never your Poynting vector x s is always going to be positive, right? So that means when it goes to negative, it's going to go positive again. So it never goes to positive. So actually, this one cycle becomes two cycle if you are calculating the Poynting vector. If you are actually squaring this, if you are squaring this, one oscillation around zero, centered at zero, is going to give you two oscillations. If you can understand what that means. Okay. Right. So that's why we end up having twice the frequency oscillation for the Poynting vector. Okay. So I think I will summarize. So I have we've discussed about the four Maxwell's equations, and in free space especially, these two terms go to zero, and then we actually have a perfect symmetry in this Maxwell's equation system, and that can lead to electromagnetic wave, because oscillating electric field, time-changing magnetic flux leads to electric field, and time-changing magnetic electric flux leads to magnetic field. So that can lead to the presence of electromagnetic waves. And we talked about how energy is stored in electromagnetic waves, because it's electric field and magnetic field, they all store energies. And because it's something that changes with time, when you are asked about the average, then you need to calculate something that changes with time. If you ask to calculate the average, then you have to average it over the time. Okay, and that will give you this kind of equation. Ends the summary lectures, all 5 summary lectures for this part. I hope I was able to clarify some of the points that you couldn't quite understand. If you have any questions, you can always contact me, try to contact me through my email, or MS Teams chats, also fine. And if you can find me in my office, that's also, you can come and ask me questions and so on. Right? So I wish you good luck with your study, and also remember you have quiz 2 that is coming up in 2 weeks or so. Good luck with that, and also with your exams. And I hope to see you around. Okay. Thank you very much for attending the summary lecture.